Okay, so the title of my talk is First Detection is in Coin Quantum Walk. Typically, I'll be talking about two aspects of this: the matrix valued renewal equation and the effect of restart. Yeah. So quantum walks have been a topic of interest for physicists, computer scientists, and in recent times, mathematicians as well. It has been applied to a lot of physical as well as computational problems, from modeling energy transfer in photosynthesis to simulating Dirac equations, and computational problems like database search and all. Also, they have been implemented in various experimental systems. Okay, a broad range of Markov chain-based classical search algorithms have an analog quantum algorithm, which has a hitting time, which is square root of the corresponding classical hitting time. That's why it has been, it is really interesting to study the statistics of a single quantum particle, doing a quantum walk on a lattice and studying how long does it take for a particle to reach a detected site. But all this study has been done numerically. No such analytical framework exists. So in this work, we have developed an analytical framework for subspace detection. I'll be talking about subspace detection, what is that? And use that framework to solve the problem of coin quantum walk. Okay, so let me first introduce what is coin quantum walk. So we have a 1D lattice, right? This is our arena. Our quantum walk will be happening on this. And of course, we have a quantum walker. We'll give this quantum walker 2 degrees of freedom, first of which is position. So it can be anywhere on the integer line. So the position space is a span of these kets, which represents the position of the particle on the lattice. And the second degree of freedom that we are going to give is some internal degree of freedom. Let's just call it spin, which can be up or down to make things simple. And yeah, and ket 0 and ket 1 will be representing the spin states. And this is the position spin space. The total Hilbert space will be a tensor product of that, and the basis states will follow the corresponding structure. Yeah, this is just the expression for a state and some general state and time t with the normalization condition. One thing to take away from this slide is the probability to find a particle at some detection at some target will be given by the probability to find that at the target with spin 0 or spin 1. So yeah, this will become more important as we go on, right? So now let's talk about the dynamics of the walk. So the dynamics is governed by this one-step unitary operator. Okay, so you apply this operator to go to the next time step. This is a discrete time quantum walk. So yeah. This unitary operator itself consists of two operators, spin, shift, and coin. Okay, let me talk about the coin first. So the coin operator acts trivially on the position space, but it does something to the spin space. So for this work, we have chosen this coin operator. In principle, you can choose different coin operators, right? Like a Hadamard or anything. You just have to follow the unitary structure and all. Okay, so this is exactly what is quantum about this walk. Like you can think of a classical walk as something like you toss a coin. And if it comes a head, you can pre-decide that if a head comes, you'll move to the right, and if a tail comes, you'll move to the left. The only thing that is quantum about this is that in this case, instead of producing a single outcome, now it can produce superpositions. So yeah, the spin state can exist in superpositions, and because of that, quantum nature comes up, right? So next we have the shift operator, which will shift the position of the walker depending upon which spin state it possesses. So let's say you have a spin up, then you'll move to the right, and if you have spin down, you'll move to the left, right? And that's all about the dynamics. So let us assume that we have a state at initial state at time t is equal to 0. We evolve it for tau number of steps, and then we do a measurement. What's the measurement? This is the measurement operator. You can think of it as a detector being placed in one of the lattice sites, which detects whenever the particle comes there, right? So the state just before the measurement will be given by this, tau time minus. Now, after tau number of steps, you look at the detector and you, what are the outcomes that you can get? So first is yes. Yes means yes, the particle was detected. And that happens with decimal probability. Second is no, the particle wasn't detected at the target site. And in that case, which happens with 1 minus p1 probability, of course, in that case, you project the state everywhere except the detection state, and you continue the walk until you do the next measurement. And you keep doing that until you detect the particle, right? So the detector will give you a series of no, 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 and finally a yes, right? And the first time that you get a yes is called the first detection passes time. In the interest of time, I won't be talking about that, but instead I'll be talking about first detection amplitude. This represents, this is the probability that the particle will be detected for the first time at the nth step, right? And this is given by this. This is very easy to understand. You have this initial state, and then you're doing evolving it with the unitary, projecting it out of the detection subspace n-1 times. That represents that for the first n-1 steps, it wasn't detected, and at the nth step, it was detected. Yeah, right. So to solve this problem, we need a renewal structure. So let me first talk about the classical passage time. You have two states, x and y, and you want to ask what is the probability that you'll reach y at the nth step, right? To do that, you first go from x to y in m step for the first time, and then you return to y in the rest of the n-1 m steps. Note that you could have visited y in these n-1 steps. Multiple times you could have visited y, right? So this is exactly what I just said, and you sum over all such m's, right? The quantum analog of this, if you talk about the quantum analog of this, we have to define some amplitudes instead of probability. So these are the corresponding amplitudes. Bn represents the first detection amplitude. Nu n is the free evolution, and mu n is the return amplitude. And the quantum analog will have this corresponding structure, which is pretty similar to what we have had in the classical case. And if we define the generating function, this will have a compact form. This is called the renewal equation in the quantum case, right? Now, what happens when you have, instead of one state, you have a subspace in the Hilbert space, which is your detector detection sites, basically. So now you have some initial state, and you have some detection subspace, which is a d-dimensional state spanned by this, and this is the projection operator there. You do a similar thing. You reach there for the first time in m steps, and then you come back in the rest of the n-m steps, right? These are the corresponding amplitudes. The only difference that it has to the previous case is that now these things won't be a single amplitude. Instead, they will be vectors of amplitudes, right? And the entries of these will be the first return to all these states in the detection subspace. Is this clear? And going by a similar calculation, we can reach to this renewal equation, which is, in the case where we have a subspace, detection subspace. And similarly, if you talk about generating function, this will have a very compact structure, this. See, we are interested in the first detection distribution. Like, what is the probability that the nth time it will be detected for the first time, which is given by this vector, right? And you can calculate this as long as this mu z is invertible, which in most of the cases, it would be invertible, okay? And the first detection probability will be given by just the norm of that vector, right? So we use this framework, the total framework, to solve this coin quantum walk problem. So why do we have a detection subspace, multiple states in the coin quantum walk problem? Because just as I said, the detector doesn't care whether the particle comes there with a spin up or a spin down. So that's why you have two detection sites. So it's a detection subspace spanned by two states. And solving this linear system of equation will give us this expression for the generating function, first arrival generating function. And these are the corresponding definitions that I've used here. Okay, so you can start with different initial conditions. Okay, one such initial condition I have showed here, but yeah, this is, you start with position 0 and spin 0. These are the corresponding generating functions. The first one represents when the target is at the negative side of the integer line. The second one represents when the target is at the positive side of the integer line. This might look complicated, but this have a structure which can be exploited to extract the amplitudes. This is for negative side of the integer line, this is for the positive side, and this is the definition that I've used here for this function ak. Right, okay, so maybe I'll talk about more interesting things. What is the large n limit of these probabilities? Okay, so these are the actual probabilities that we see here, right? And these are the asymptotics. So we see that both of them follow this power law, this n cube decay. In contrast to the classical case where we have a n to the power minus 3 by 2 decay in probabilities and have oscillatory coefficients to it, right? Okay. But why do we even do a quantum walk? I mean, you would want your particle to be eventually detected, right? So let's talk about total detection probability. What is the probability that the particle will ever be detected, right? So this is the total detection probability up till n steps. You just sum up all the first detection probabilities. And these are the corresponding plots that we have got. Okay, so when the target is at the negative side of the target line, we see that spin 0, that is the spin down state, performs best. And when it's the positive side, the spin up state performs the best. Right, but still, I mean, there's some non-zero probability, or I would say, I mean, there is considerable probability that the particle would never be detected at the target side, right? Because it saturates, I mean, even in the best case, it saturates around 0.5, right? So there's a very high probability that the particle will never be detected. So what do you do in that case? So you introduce the sharp restart strategy. What do you do in that? You let the walk go on, and you restart the walker after every R null measurement. So some pre-decided number R you have decided before the walk. There are some rules or basically methods to decide what R is best for the walk. I won't go into that. Let's just say there's some R, right? And you restart the walk after R no measurements. So R times you go no, you bring it back to the initial state, right? This is what is happening here. Yeah, this is what is happening to the wave function. The wave function is evolving, and after R null measurement at the target side, you bring it back to the initial state. Okay, so in the case of a restarted walk, these are the first detection probabilities. The first term over here is nothing but the survival probability. So what is the probability that your walker survived the first cycle? Well, each cycle represents each time you restart. Each time you restart, one cycle is complete. So yeah. So you just, this is how you define the first detection probability in the case of a restarted walk, and these are the plots. So this is when the particle target is on the positive side. This is when it's on the negative side. You see that eventually the walker will detect the target in case of a sharp restart strategy, right? And the similar structure is also there, like in the case of positive being on the positive side, target being on the positive side, spin 1 performs the best, and spin 0 performs the best when target is on the negative side. Yeah. So that's all, and thank you so much for listening. I'll be happy to take questions.
Any question?
Mentioned these two operators, the S and C, the coin operator and the S operator, right?
Yeah.
The shift operator. So for the coin operator, I can imagine some hard-mart gate or something.
Yeah, sure.
You can implement. So what is the sort of analog, physical analog of this shift operator? Like how the particle moves from one lattice side to another lattice side.
Like in continuous time models, people use use this hopping Hamiltonians and things like that.
Yeah.
The classical, I mean, when you talk about this classical random walk, you can think of it like this: like you toss a coin, if you get a heads, you move towards the right. You need an analog.
I'm just trying to think, since here the time you have discretized the time.
Right.
What sort of Hamiltonian would the system have? Because this shift operator in some sense it's the Hamiltonian, right?
Right.
Because it is like just moving. So in this discretized case, what sort of like Hamiltonian that we will get?
I'm not very sure of that. I mean, whether you'll have a Hamiltonian structure, but yeah, maybe you can. Yeah, but I'm not very sure about the Hamiltonian structure. Like in the case of continuous time walks, you have this hopping Hamiltonians and things like that. This is basically analog of the classical Markovian walk, basically. Yeah, but I haven't explored what kind of Hamiltonian can you put up in this?
Like for the classical case, we have, in some sense, like some physical example, like someone walking or some other thing. In the quantum case, usually the evolution is in some sense like unitary.
Right, sure.
The evolution is unitary, and now the evolution is happening in time, and time is discretized. We have to have some sort of Hamiltonian.
Right. Yeah, I'm not very sure. Maybe we can talk about it. Maybe spin, up and down, yeah. Oh, sorry. Plus is a superposition of spin 0 plus spin 1. A linear superposition of these two spin states. I'm sorry I didn't mention this.
Then let's thank Ashif.
Thank you so much.